we're going to start talking about some techniques for conditioning hard-to-solve cases. What this comes from is invariably what you'll find with different load flow software sharing file formats and so on, and being able to load other file formats from other software. It doesn't always mean that the settings and options and conditions get translated from one to the other, or one software package will treat an option a little differently than another, and so that might lend itself to some solution problems when you first start working with a new case. And so we like to give you some techniques and some ideas and some things that you can look for that will help you take a case that, if you just load it in and hit solve, might have some problems with it. It will help you figure out what some of those problems might be and how you can take care of handling that. So for example, we've got some example cases solving real power flow cases. We have a low impedance mismatch case called initial mismatches.raw. We have a controller settings and area control case called unspecified interchange.raw. So there are several different cases that we can use that are examples here. We can make use of the check immediately option for generator var limits in a case called check megavar or check var immediately.pwb. We can look at a loss of reactive support, voltage collapse, and low voltage solutions in a voltage collapse.pwb case. And this example uses what's called a robust solution process in the voltage collapse case. I do believe that the robust solution process is on its way out, but for current versions of simulator and some of the examples that you might see in some of these slides, we can still talk about it. But I believe going forward in future versions of simulator, you might see that robust solution process be removed. So what do you do when you're reading a solved text file-based public power flow format and you get that case that someone supposedly solved, but when you load it into simulator, it doesn't solve? There might be issues with the initial case. There might be large mismatches on low impedance lines. That's usually not a real big problem. That can be handled. Voltage controllers such as transformers and switch shunts, maybe they were on control, maybe they weren't in the original case. We don't really know that in some situations. And area interchange control. Oftentimes we don't know, was the initial case solved with area interchange control turned on or not. These are not errors with the case, and they're not errors with simulator either, but you do need to kind of understand what they are, because it may require you to have some interaction with the setup of the low flow solution before you try and solve it for this model when you load it in. So in the case of the very large initial mismatches, this is typically okay, because primarily it's caused by low impedance branches. Other software treats branches below a certain threshold impedance as exactly 0, and the buses at either end of the branch are then merged and the transmission line is ignored during the course of the solution. In simulator, we don't merge buses this way. We do have a minimum R and X value, however, so do be aware that you cannot set values for R and X below these values, and that's just for solution and numerical stability. We want to maintain those minimums. So if you want to look at a case with initial mismatches, we can open simulator and open a case called initial mismatches.raw. We're going to go ahead and go out of this for a second and go back to simulator 19, which I have running. If you don't have it running, you can should be able to run that. And I'm going to open a case. So I'm going to file, open case. And the case I'm going to open is a raw file, so I'm going to go down and change the file type from PowerWorld binary to PTI raw data. And then the case I'm interested in is in the S03 getting a case to solve folder. That's right here. So I will open this, and there's 2 raw files in here. The raw file I'm going to open is the raw file called initial mismatches.raw. So I'm going to select that file and click open. And I'll see in the log that it will tell me that it has opened the file with some messages about how it handled some devices. I'm going to close the log now for the moment, and what I'm interested in is I'm going to come over here to the Model Explorer, and I want to look at the initial mismatches in this case. So I'm going to go under Network. There's a Mismatches display. I'm going to select that and look at the initial mismatches in this case. Notice that the mismatches on some cases are pretty large. If I take a look at it, some of them seem to be in pairs, where there's an equal and opposite value. For example, these two here that are side by side, we have bus 80049 has a mismatch of minus 1567.4 megawatts. And right next to it, at 80053, we have 1566.34. That's not uncommon, and what this typically indicates is that these two buses are separated by a branch with very low impedance. In the PSSE software, the low impedance branch was ignored. The two buses were treated as the same bus, so they are read in with the exact same voltage and angle. But in simulator, we're not ignoring the branch with the low impedance, and because of that, the two buses should not have the exact same voltage and angle by our reckoning. Therefore, we come up with a mismatch on those two buses. And the mismatch can be fairly large because you're talking about a voltage, two voltages that are exactly the same with a very small impedance. Because the impedance is very small, the mismatch is going to be very large. So that's where you'll see several pairs of buses that all have values of mismatch that are about the same in magnitude but just opposite in sign. Notice though that the two at the top, it's not immediately apparent that there's a equal and opposite. And so at Bowmanville and Clairville, we actually have more complicated processes or more complicated situations because of what I'm about to show. If we go look at a display for this, we're going to open a one line that was set up for this case. So I'm going to go to File, and I'm going to go to Open One Line. And there's a one line that we already created called the Bowmanville-Darlington.pwd file here. So we're going to open this display file. And this is a display, a one-line diagram that we set up for this specific Bowmanville situation. And what we see is that we have the Bowmanville bus that has a mismatch of minus 3373.97 megawatts. And we saw that reflected in the mismatch table over here at the top. So it was our largest megawatt mismatch. We didn't initially see an equal and opposite magnitude mismatch, but the reason is that there are actually four different zero impedance or near zero impedance branches that connect to four different Darlington buses. They are all still zero impedance branches, but their mismatch at the other end is actually split up across four different branches. So you'll see all four of these mismatches here. If you take these four numbers and add them up, you're going to get a number very close to this number right here. So it is still, in fact, a zero impedance branch mismatch that we're seeing, even though it wasn't initially apparent here in this situation. So drawing out this little diagram has helped us understand that. I'm going to open another diagram for Clairville to also see what's going on in Clairville and see if it's a similar situation. So I'm again going to go to Open One Line, and I'm going to open the Clairville.pwb. And again, it looks like I have a similar situation of 6 branches going to 6 different buses, all with impedances that are very small. And I have, again, 6 values of megawatt mismatch at these 6 Clairville buses down here. If I add up all 6 of those, I will get a value that's very close to magnitude-wise this value of mismatch here, which reflects the value I saw at the top of my mismatch table over here. So in all of these situations we've examined so far, they actually are all related to zero impedance or very near zero impedance branches and mismatches across those, because we are not removing these low impedance branches from the solution, we are including them, and yet the voltage and angle at each of these buses as well as this bus are all being treated as identical, which is where the mismatch across these branches is being generated from. So if I go back to my initial case, and again I'm just going to pull up the mismatches so I can see it, but I'm going to go in and I'm going to do some changes to my settings before I try and solve this case. So I'm going to go to case information and I'm just going to go to simulator options. And then what I'm going to do is I'm going to look at this section right here, disable switch shunt, and I'm going to turn off these control options. So I'm going to disable all the control options. The other thing I'm going to disable is the automatic generation control as well. This is the area interchange control for the case. So it's not going to try and solve the ACE equation for each area. Instead, if there's any generation adjustment that occurs, it's all going to be handled by the system slack bus only. What I'm trying to do is eliminate the possibility that there's area interchange discrepancies to start with, and I'm also trying to eliminate that there are any issues with parallel transformer taps, switch shunts that are violating their VAR limits, so on and so forth, by just saying don't try to regulate or control any of those devices initially. And this is a common thing you might do when you load up a case and try to solve it and it doesn't solve. Reload the case, come in here and turn off all of these options. When you do that and then you do a solution, you're really cutting it down to doing, for the most part, just the inner power flow loop with the Newton-Raphson solution in it. You're removing a whole bunch of steps from the middle loop with the control devices, and you're removing the outer control loop by turning off the generation control. So you're trying to simplify your initial solution. So if I go to close the options and open the message log so I can just see the log here, and I'm going to right click and I'm going to clear the window just to wipe my log for now so that I can see what it's doing. I'm going to go ahead and do a single solution on this. So I'll go up and do a single solution. I can do it either here, single solution full Newton on the tools menu, or there is a quick access toolbar button up here as well. So I'm going to do a single solution, and it's going to go through and do some iterations of the inner power flow loop. I will also notice that there was some generation VAR limit being handled, and that is because generation VAR handling is done in the inner power flow loop. So I will see some messages regarding the generation VAR adjustment. So I see some generation VAR adjustment going on and some iterations of the inner power flow loop. And it goes through 6 control loop iterations. So 6 times it went through and checked VAR limits and recalculated the inner power flow loop. We finished in about 1.5 seconds. And if I go over and look at my mismatches, I'll see that my mismatches have all gone to 0. So what it has done, the mismatches have been resolved. We've calculated the actual voltage and angle at each bus that was initially in the original case. They were all the same, voltage and angle. And we have now calculated what they actually should be with these low impedance branches included. So now we can see our mismatches here are 0 at both ends of the Clairville lines. And we can also look at the Bowmanville to Darlington lines and again see that the mismatches have gone to 0 for this solution. So simulator handles these lower impedance branches and calculates the voltage and angle difference at the terminal buses on both ends of the 0 impedance branches. PSSE does not, so that's why when you load a raw file you will a lot of times see initial mismatches. If we look at another example here, or continuing looking at this example, I believe, if we look at what happened or why we turned off a bunch of the options, I'm going to go back and look at some slides here so we can talk about why we turned off a bunch of the options that we saw. we saw these displays and what the mismatches were, and I went in and I disabled all these options. So we removed the mismatches due to low impedance branches without moving any controllers. So we turned off all these devices, we did a single solution, and we removed the mismatches. Now we can start gradually restoring the voltage controllers. So we can turn on the switch shunt controls first, then solve the power flow, turn on SVCs, solve the power flow, turn on LTCs, solve the power flow, and so on. And why would problems occur? It depends on the controller settings in the original software package. So if this came from PSSE, we don't know necessarily how PSSE was treating all of these control types or control settings in the software. They may have had some of them or all of them turned off. So you might see problems or changes going on when simulator solves as we turn these on because they were not enabled in the original load flow that was solved in PSSE. So what happens for this example? So let's go back and we'll start enabling these in simulator and solving the power flow again. I'm just going to close these two diagrams, and I'm going to go back to my options, and I'm going to say let's enable switch shunt controllers first. So I'll uncheck that, and I'll go do a single solution. And if I look at the log, I'll see that during the solution process there were some switch shunts that were adjusted now, but not too many. So it did do a little bit of some shunt adjustment on a few shunts, so the shunt adjustment was performed. If I go to enable the SVC control and solve the power flow, I don't see any changes, so there were no SVCs in the case that needed to adjust. I'll go and enable the LTCs and do a single solution for that. And now I see a lot of adjustment going on. So that tells me that I had several LTCs that had to adjust. It could be that they were not turned on in the original case. It could be some of these are because the transformers, when they were read in from the case, had overlapping ranges that needed to be adjusted, or it could be that some of them needed to be balancing. Here we see some were balancing a parallel LTCs that had different taps in the original case and needed to be balanced. So there's a lot of transformer messages going on here. So we can see that there were a lot of tap changing issues going on. If we had tried to solve this case initially with all of the initial mismatches and all of these transformer taps changing and all of the shunts changing, the Newton rafts and load flow might have had trouble resolving it because of everything that was getting changed all at the same time. So that's why we often tell you, go in and turn all of these things off and then gradually turn them back on until you get a simulator solved case with everything turned on, and then when you save it from that point forward, you should be good to go. So again, we can go back in and turn on phase shifters. So I'll go ahead and do a single solution for that. And I saw, it looks like maybe one phase shifter that may have changed. So there was a phase shifter that did adjust, but not too much adjustment going on with phase shifters there. So we've gotten to the point now where we've re-enabled everything except for the generation control. Before we try to enable the AGC, we need to make sure that the case truly was solved while on AGC control. The best way to check that is to go to the Model Explorer and go to the Aggregations group and look at the areas. So that's if we're looking at the Model Explorer here, we go down to Areas, and we look at the areas, and of interest is to look at the ACE column. So we look at this column right here, which currently is grayed out because I have set to disable the area generation control. But we look at the ACE column. If the values are really large, the original case was then not solved using area control. In this case, they look okay for this initial mismatches.raw case because the values are relatively small. You know, I see one that's 11 megawatts. That grand scheme of thing, in a large case like this, that's not that much. Here's one that's minus 16. So they're not that big. The ACE values are not large. If all of these were really large numbers, that would be an immediate indicator that this case was not solved with generation control turned on. Instead of solving this with generation control turned on, let's go look at a case that is not solved with area generation control initially. So let's go open a new case. So we're going to go File, Open Case. And again, it's another raw file we're going to look at. So we're going to go to raw format. And we're going to choose the unspecified interchange.raw. So we're going to open this. We don't need to save the original case. Okay, so we've opened the unspecified interchange case. And we're going to go again to the solution options. So simulator options, and we're going to disable automatic generation control. Say OK. And open the log so we can see the log. I'm going to clear mine just so I don't have anything else in it right now. And I'm going to do a single solution. And it solved fairly quickly. There was just 3 transformers that it balanced some taps on, but it only took 2 control loop iterations to solve the load flow. So it was pretty much solved with just a little bit of transformer tap balancing going on. Okay, so now if we go look at the area table in the Model Explorer and look at the ACE column, I see something much different in this case. Here, the ACE values are very large. That's an immediate indicator that this case is not solved. On top of that, if I go look at the unspecified interchange over here, I'll notice something about these values. Typically, for the interchange in a case, it should sum to 0. Because if it doesn't sum to 0, then your power flow isn't balanced. Because you can't have an excess of interchange or generation or an excess of load. They have to be balanced. So that means the total scheduled interchange for the entire case should be 0. And I can see here that my total scheduled megawatts is reflected by my unspecified megawatt interchange, which by saying it's unspecified, it just means that each area knows how much it should be importing or exporting, doesn't necessarily know who it's coming from or where it's going to, just how much it should have, which is all it needs to know in order to balance itself. But in this case, they don't sum to 0. If I right-click and I go to Set Toggle Columns and I go Get Column Metrics, that tells me what the sum for this column is, and the sum is definitely not 0. It's negative 166.56. So there is an excess of 166 megawatts of import in this case that cannot be accounted for. If Simulator tried to solve this right now, it would try and make up for that difference at the slack bus, which is never a good thing. And it would tell you in the message log that you have an imbalance in the system interchange. So we know in this case that our case solves when we're ignoring generation control. So that most likely means that the case was solved in PSSE ignoring the interchange control. So these interchange numbers don't really mean anything because they were ignored in the original case. So what can we do about that? Well, we can look at the aggregations and go down to the megawatt transactions table. We can open this up. And in the toolbar, we can choose records and we can choose clear transactions and auto-insert tie-line transactions. All we're doing is we're wiping out any interchange that's currently specified in the case and replacing it with tie-line flows. So any tie lines between areas, we're now going to set up transactions in such a way that every area will have a balance based on just the tie line flow that's currently calculated between them. So I'm going to go ahead and click that. So it's going to wipe out any previously specified interchange, and it's going to replace it with interchanges reflective of tie line flows. So it will list transactions here going from area A to area B and how much. And that's that's what the tie line flow was between these two areas. So it will establish transactions between all the areas based on what the tie lines between those areas were. So that's one way to go ahead and generate some tie line or area interchange flow values so that when you go back, you can calculate this now with the area interchange turned on, and you should have the same solution. Another thing you can do is to set the unspecified interchange equal to the actual interchange. So if you go to areas, if I go here to areas, and I go over to the unspecified megawatt interchange column here, I can right click and I can go down to set toggle columns, and I can say set all values to field. And then I can choose a field that I want to set this to. So I can go down to the interchange group and I can choose the actual megawatt export and click OK. And it's going to tell me that it's going to change all values in the column to the new value of the bus group interchange megawatt. And I can say yes. And what that's going to do is it's going to take all the interchange megawatts that I had specified by the tie line flows, and it's going to instead plug them in as the unspecified megawatt interchange. Now in this case, that's not necessarily good because I've just doubled up my interchanges. But I can again just wipe these out, set toggle columns, set all values to, change them back to 0 if I want, and that'll set them all to 0. So there's just a couple of options for how you could have set up these interchanges. The option I've done currently that you're looking at is I've set them all up based on the tie line flows. The other option I had, rather than doing it based on tie line flow, is I could have just come in here and right-clicked and set all values to field and set all the unspecified megawatt interchanges to the actual interchange megawatt, and that would have balanced them out. So right now they're balanced anyway because I established transactions equal to the tie line flows. And I could solve this now. Before I do that though, not before I do that, but I can rather, before I solve it, go turn on the option to allow automatic generation control. And I can go look at the log and do a single solution, and I should see no difference. Because all I've done is I've wiped out the original transactions, which made no sense in the case. They weren't balanced, they weren't used. I've wiped them out and replaced them with transactions that reflect the tie line flows of the originally solved case. So what I've done here is I've made it so that I can, going forward, solve this case using generation control by plugging in these transactions that are equal to the tie line flows. That gives me a case that is solved, and yet I can turn on generation control. I could now go and start changing transaction amounts or changing loads in the areas and solving the case and having the generation follow the load. Whereas originally I couldn't do that, leaving the case the way it was because it had not been solved with generation control and the interchanges were unbalanced. So the next thing we're going to talk about is check immediately for megavars. So how do we use generators? What do we do to use the generator megavar check immediately option? Normally inside the inner power flow loop, the choice about whether a bus is PV or PQ is not changed. So for that internal inner power flow loop, we don't on the fly change is the bus PV or PQ right away. If a bus is considered PV, it's allowed to inject and absorb unlimited megavars. And if a bus is considered PQ, its Q output is fixed. The choice to switch between a PV and a PQ bus is normally made in the voltage control loop, or the middle loop. The check immediately option for the generator megavar limits changes this. Choosing this means that buses with voltage controlling generators or continuous switch shunts will check whether they hit or back off a limit after each inner loop iteration. And this may help in some situations with a solution, however, it will slow down the solution process. So if I go back to Simulator and now open another case, I'm going to go to File, Open Case, and this time I'm going to open a PowerWorld binary file, so I'm going to leave it as PWB, and I'm going to open the checkvarimmediately.pwb file. And I don't need to save the existing case. So now I have a PWB file that we have specified that we are going to create an issue with the vars that we can then try and rectify using the check vars immediately. Okay. Note that the set point voltages are all 1. So our set point voltages are all 1 per unit for these 4 generators. The terminal voltages are all 1.02 per unit. And all generators are stuck at their minimum megavars. They're all at 0. Okay, so that's where we're starting at with this example. So if we take the branch labeled open this out of service and hit single solution, we get an unsolved power flow. What about the generator megavar support? Notice that all generators are still operating at 0 megavars, so none of them have tried to move. The power flow started with the generator buses flagged as PQ buses because they started at their minimum megavar. If they were operating with more VARs providing more support, they might have prevented the collapse, but the inner power flow loop did not achieve solution, therefore the generators did not have an opportunity to go into the voltage control loop and switch to a PV bus, which would have helped provide the VAR support. So we can use the check immediately option in the simulator options to achieve a solution in this situation. So first of all, let's restore back to our state prior to the failed solution. And there's a handy tool for that. If we go to Tools, Restore, we can actually restore the state before the failed solution attempt. What this will do is it will take all the state variables back to where they were prior to the solution. So I'm going to restore that. Say OK. Note it didn't reopen the line because that was something I had done prior to the solution. It only restored all the voltages and angles back to where they were just before I hit single solution previously. So the line is still open, but this time before I do a solution, I'm going to go into the options and I'm going to check the box to check immediately for the VAR limits. So now if I hit single solution after clicking OK, it's going to allow the inner loop to check the VAR limits and change the status of the generators from PQ to PV during the inner power flow loop instead of waiting until the inner power flow loop has finished. So I go ahead and do a single solution, and sure enough, it has changed the buses all to PV, and it has dispatched the VAR output of the generators and maintained voltage support. So this is an example of where all these generators were at their limit for VARs, and because they were at their limit when we tried to do a solution for this special case, the inner power flow loop failed to reach convergence, which gave the generators no opportunity to actually change their VAR output because it did not change the terminal buses of the generators from PQ to PV during the solution process. That would have occurred if the inner power flow loop had at least reached one valid solution. Then it would have gone to the control loop and it would have changed the generator types or the bus types from PQ to PV, and the generators would have dispatched, but it never got that far. By changing the check immediately option, we have allowed it now to change the VAR output immediately during the inner power flow loop, and therefore we get a valid low flow solution. It probably took more iterations. In theory, it took more iterations to reach a solution because it had to adjust those VAR limits on the fly in the inner power flow loop. But in this small case, you probably don't really notice that. In a bigger case, you might notice that it takes longer to solve because it does check the VAR limits every time it solves the power flow in the inner power flow loop. And that takes a little extra time to do. So now let's look at a voltage collapse example. And I'll go back to a slide for a moment and we'll take a peek at what we're going to talk about here. So in this situation, we're going to look at a case, an ERCOT, where we have a region of the low flow that the voltage is collapsing. And we've contoured a one-line diagram of ERCOT to give us a feel for where we're having the voltage problems. And you can see that from our color key over here that we're getting voltages at 0.8 per unit and below in this region of ERCOT. So we're going to try and figure out what's going on here. And we can do that by opening another case called voltagecollapse.pwb. So I'm going to go File, Open Case, and open voltagecollapse.pwb. And I'll close my log. And here's my case. Here's my diagram. I'm going to try and do a single solution on this, so I'll open my log, hit single solution, and it fails to solve. And I can see here it tells me where my mismatches still exist, but that's not necessarily helpful to me because I don't know where those buses are located in the case. So what I can do is plot the contour. So I can go to One Lines, Contouring, and I'm going to hit Recalculate Contour. So it calculated the contour, and it's not as dark here as it is on the slide, but it does show me down in this area is the darkest area. So this area down here along the border here in southern Texas is where I'm having voltage problems. So I'm going to go ahead and just remove this contour for the moment. So I'm going to go back up to the One Lines tab, Contouring, and I'm going to hit Remove Contour. And then I'm going to go to a saved view that we've saved on here called Laredo. And what a saved view is it's just a location on the diagram and a zoom level on the diagram that I was looking at some particular point in time, and then I saved those settings of the location and the zoom level. When I saved it in my saved view list, I can go recover it from my saved view list at any time by name, so I can hit Laredo, and it takes me directly to a location and a zoom level on my diagram that I was looking at before. So in this case, I'm looking at Laredo, and this is the location where I was having voltage problems. Because you see I have voltages here that are in the 0.71 and 0.72 range. And also, now that I've looked at this diagram, and by diagramming it out and using a contour to try and pinpoint where my low voltages are, I can zoom in and notice that I have shunts available at these 4 locations, but they're all out of service in this case. So I have reactive support, but it's not online. So what happens if I close in this shunt at Laredo and supply some VAR support here? I can do a single solution, and lo and behold, if I look at my log, I got a solution. However, if I look at my voltages, they've actually gone down. So what I just did was get a solution, but I got the wrong one, because my initial guess was so close to the nose point of the curve that when I made that selection and solved it, Newton-Raphson actually went to the low side of the PV curve instead of the high side for these buses. And so I'm now solved, but at a low voltage solution in this region of the case, which is not necessarily a good thing. If I go look at the sensitivities option on the tools menu, I can go look at sensitivities and go down and calculate flow and voltage sensitivities, and then go to the self-sensitivity tab here. If I go if I go to self-sensitivity and calculate sensitivities, And then I'm going to sort here on the DVDQ. I'll see that I have several negative values of DVDQ, including at bus 8290 right here, which is Laredo, where I just put in that shunt. And what that negative DVDQ is telling me is that as I increase the reactive power, the voltage is going to go down. So by looking at these sensitivities, I've just verified that I am in fact on the low voltage side of the solution, because these numbers should be positive if I'm on the high voltage side, because what you want is your voltage to go up as your reactive power goes up. What I'm seeing here with the negative number is it's telling me the voltage is going to go down as the reactive power goes up, and that's not a good thing. So we're verifying, looking at the sensitivities, that we have gone to a low voltage solution. So if we go look at determining the location of the negative DVDQ buses, I can go look at what's called determine path distances to buses. So I can go look at connections here and determine path distances to buses. So we'll open that. And the bus we want to select is 8290, which is Laredo, where we changed the Mvar injection. So we're going to select Laredo. We're going to calculate the distance measure by magnitude of the impedance. So I'm going to change the distance measure over here to absolute value of Z. So basically what we're doing is we're going to use as a distance measure the impedance of all the branches. We're going to calculate it only for closed lines, because we don't necessarily care about open lines in this case. We only want to know what it is across closed lines. And it's going to populate what's called the custom field floating point 1. So it's going to calculate these values, and it's going to plug them into custom floating point 1 in our table. So if I go ahead now and do calculate, it's going to put custom float 1 in here, and it's going to calculate these values for path distance to buses. All right, so now custom float 1 is populated with those values. If I go back to my negative DVDQ values over here, and I use display column options, so I right click and go display column options, and I'm going to add the custom floating point 1. So I go down to the custom floating point 1, and these are the distances we just calculated, the path distances from the bus where we inserted the shunt capacitor. I'm going to drag this out and place it, so you can just left click and drag it over. So custom floating point 1 is in, and we go OK, and we can see our distances here. And of course, at bus 8290, the distance should be 0, because we're at the bus where we inserted or did the calculation from. And then we can see a number here that what this really means is the smaller this number, the closer these buses are electrically to the bus where we inserted the shunt value, or we turned on the shunt. And so all these negative DVDQ values here are probably going to have numbers that are fairly small, because electrically they're near the bus 8290 where we put in the VARs. So sometimes a flat start followed by a robust solution process can help you achieve a successful solution. So we can try that. So if we go to the Tools menu, and I'm going to close these dialogues for now. If I go to the Tools menu and go to Solve, there is a Reset to Flat Start option. So we can check that. And by default, it's going to set the voltages equal to the set points and angles, to the set point voltages, and the angles equal to the slack angle. And we're going to just leave all these others unchecked for now. We're not going to mess with changing taps on transformers or anything like that. So we're going to click OK, and we've just reset to a flat start. As I mentioned previously, this is not often a good idea for larger cases. Sometimes it works, but more often it doesn't, to just try and do a single solution at this point. So instead what we're going to do is we're going to do a robust solution. So we're going to go up to, again, the solve, and there's a robust solution process option down here. And we're going to go ahead and solve that. And it actually does come up with a solution. So let's take a look at our bus voltage contour now. So in order to do that, we want to go back to looking at all of Texas. So we're going to go to One Lines and Save View and go back to All Texas. So get all of Texas back in my display here. And we're going to go do our contour again. So we're going to recalculate our voltage contour. And now our voltages are much better. We don't have that pocket down here of low voltages. They're still relatively low, but they're in this range of 0.92 to 0.95, somewhere in that area now, as opposed to previously they were down below the 0.8 range. So by reset to flat start and a robust solution here, we have actually gotten the load flow back to a solve state and back to a high voltage solution. And again, we can look at Save View and go back to Laredo and just verify that we have, in fact, gotten voltages that are now in the high voltage range instead of the low voltage range. But it did take a little bit of massaging and some application of some local Mvar support in order to get that back to a high voltage solution where we want it to be.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.